All right. Hello there, and welcome to Astronomy Time with UACNJ. Uh, Thank you all for tuning in. I want to also big shout out to you guys. We're two away from 200 subscribers. Right. Our tonight's presentation is Buzz Aldrin, Rendezvous. That's how you pronounce that, right? Right. Our speaker tonight is Chris Mauro. He is a retired information technology executive who has managed and designed and developed business system solutions, including mathematical models and simulations. He's an avid amateur astronomer and photographer and has pursued additional education in science, history, and astronomy. He joined the North Jersey Astronomical Group in 2016 and has since participated in community outreach and public telescope viewing events. He's developed and presented talks on the history of events leading to the first manned lunar landing and orbital dynamics and the contribution of Buzz Aldrin. He is currently a member of United Astronomy Clubs of New Jersey. And with that, Chris Morrow, you can take it away.
Thank you, and good evening, everyone. Welcome, and happy vernal equinox. Tonight I will be presenting the basic concepts of orbital mechanics and discussing the contribution made by Buzz Aldrin that earned him the moniker of Dr. Rendezvous. But before I begin, I'd like to thank the officers of the UACNJ for inviting me to speak tonight. And I'd also like to extend a very special thanks to Dr. Mary Lou West for her mentorship and encouragement in preparing this project. When I began this project, I had somewhat of a neutral opinion on Buzz Aldrin. There we go. Okay. Lost my place there. Here we go. As I learned more about his life and accomplishments, I grew to appreciate his contributions to the science of space exploration. I hope that you will feel the same way at the end of this presentation. The material presented is somewhat technical. I will keep it simple and as brief as I can, not to dwell on the formulas and calculations, but just enough to appreciate the mathematical foundation supporting the science. Besides, it's been a long time since I worked with calculus or differential equations, so I doubt I could answer any questions anyway. I will focus on the history, the people, scientific concepts, as well as their application to the current state of space exploration and operations. And of course, if you have any questions, you can use the chat box to enter your questions, and we'll take them one at a time. The exploration of space continues today, and we're excited about the latest unmanned rover to explore Mars and the prospects of crewed missions to put more footprints on the surface of the moon, and of course, eventually Mars. So the question is, whose idea was this anyway? And how did we get here? In literature, the idea of space travel to planets originated in the 1st century. A writer named Lucian talked about a battle of worlds, Mars battling the moon, battling the Earth. Wild stuff for the 1st century. It later became more popularized by Jules Verne in the 19th century, and eventually by movie makers and science fiction writers in the 20th century. But the unofficial start of the space race or space age began with the launch of Sputnik in 1957. This was the first step toward making human space exploration a reality. The second launch a month later carried the first living passenger, the dog Laika. She was a stray from Moscow that they picked up and put her in a little capsule. And thus the space race began under the backdrop of the Cold War between the USSR and Russia. Sorry, I got carried away with this. I gotta go back. Here we go. Hold on. There we go. Okay. Sorry about that. Okay. The scientific foundations necessary for space exploration were initiated over 400 years ago with the definition of the orbit by Johannes Kepler. I love this little cartoon. It shows that people were not quite ready for what he was talking about. So you see that the orbit of a planet is elliptical, and one person says, what's an orbit? What's a planet? And what's elliptical? So going back to high school geometry, this is an ellipse. An ellipse, pretty much by definition, has two focal points. And it's a path where the sum of the radius from each focal point is the same. It's constant, no matter where you are on the ellipse. There are two axes defined, unlike a circle, which has just a diameter. An ellipse has two axes, a major axis and a minor axis. The major axis is longer than the minor axis, and the semi-major axis is half of that. The center of the ellipse is the center between the two focal points. It's a lot of fun to construct ellipses at home. You take two map pins or two stationary objects, a piece of string, loop them around both, take a pencil, and you can trace a number of different ellipses. And you can see how the ellipse changes based on the position of the focal points, the length of the string, and so on. The eccentricity is an important value. It defines the elongation of the ellipse. And let's look at eccentricity a little closer. What we have here are the conical shapes. And within each of the conical shapes, we have a curve. And they're portrayed in a gravity well, which is a good way to look at this, because you'll see that the first one, which is a circle, is bound within the gravity well. The one to its right, which is an ellipse, is also bound to the gravity well. Yet the first one below is a parabola, and it is goes outside of the gravity well, which means it's an escape. Excuse me, it's an escape trajectory, as is the hyperbole. So both of them would be escape routes or trajectories. Mathematically, eccentricity is 0 for the circle, between 0 and 1 for the ellipse, equal to 1 for parabola, and greater than 1 for hyperbola. Johannes Kepler, a student of Tycho Brahe, postulated the 3 laws of planetary motion based on Brahe's observations. Brahe was one of the last astronomers to do naked eye observations. He did not have a telescope. So the first law of planetary motion is that all orbits are elliptic. They can be circular, so there are special cases. But here the orbit sweeps equal areas at equal time. And this is a concept that's important to understand. So when you have this area A1 and area A2 and area A3, the satellite or object, a planet in this case in the diagram, will trace from A to B in the same time as it does from C to D and from E to F. So you can see the velocity is going to have to change depending on where you are on this ellipse. The orbital period, which is the time it takes to make one complete orbit, is proportional to the semi-major axis of the orbit. The longer the semi-major axis, the longer it will take to complete the orbit. Then about 80 years later, Newton applied the laws of gravitation and motion to objects in orbit, where the centrifugal force, Fc, and the gravitational force, Fg, were the same, because at every point in the orbit, these two would balance. So by solving for this equation being equal, You come up with the velocity in the orbit as the square root of the gravitational force times the mass of the planet you're orbiting around, divided by the radius. And that's for a circular orbit. The radius is measured from the center of the mass, not from the edge. And so what you get is approximately 17,500 miles an hour as an orbital velocity. And that's equivalent to about 4.85 miles per second, which is a number to think about for a minute, because imagine, you're at Jenny Jump at exit 12, and you're traveling at orbital velocity. 3 seconds later, you'd be in Rockaway, New Jersey. I think that would be great for your commute. That would make things very easy. It's important to note, though, that these equations these are simplified. They're not used in the calculations of orbits, because Einstein's equations of general relativity, where gravity is due to curvature of space-time, provides a more accurate calculation. So that's what's used in the industry. So this diagram gives you a kind of an idea of the difference between the potential energy and the kinetic energy, which is that balance between the centrifugal force and gravitational force. And you see with a circle, it's essentially the same no matter where you are in the orbit. Here, elliptical orbit, when you're at apogee, or the furthest point from the from the body you're orbiting, your potential energy is higher, and then it will be reduced as you come around, and then it'll increase again as you go back out to apogee. It's kind of like the way the Earth's orbit looks. It's elliptical, not extremely eccentric. We don't have a very elongated orbit. And today we've crossed the vernal equinox. So the sun is now crossed the equatorial plane and will be in the northern hemisphere. So based on an elliptical orbit, you can calculate the velocity equal to this formula here, the square root of the gravitational mass times the size of the mass of the Earth, times 2 divided by the radius minus 1 divided by the semi-major axis. And compare that to the velocity formula for a circular orbit, which does not involve a semi-major axis. Then the period is defined as the following equation, and I won't go into too much detail on that for now. So the basic rules of orbiting, the velocity of an object in orbit is not a function of the mass of the object. So whether it's the space station or whether it's Sputnik, the velocity would be the same depending on the radius or the altitude of the orbit. The velocity of an object in orbit changes inversely to its distance from the central mass. So the greater the distance, the slower the speed. And it takes, the time it takes for an object to complete an orbit is proportional to that semi-major axis. The larger the orbit, the more time it takes to orbit. So the spacefaring nations of the world have agreed and defined a geocentric equatorial coordinate system. Every presentation should have a very complicated diagram in it, and so this is my complicated diagram. So this gives you a pretty comprehensive view of all of the parameters that are used to define exactly what an orbit looks like around the Earth. There are currently some 19,000 satellites that are in orbit, with plans for hundreds and hundreds of more for communication purposes and other purposes as well. So keeping track of all of this is a tremendous job. So just quickly, the parameters we're measuring are the semi-major axis, the eccentricity, the inclination of the orbit, the right ascension of the ascending node, the argument of perigee, and the time or period of the orbit. Okay. Now, there are various types of orbits. So let's go over a little bit of the taxonomy of orbits. This is not a comprehensive list. It's a basic, structure, because there are dozens and dozens of other variations. But we start with circular orbits at various altitudes, and they're pretty simple. Got a good example there. Geostationary orbits are orbits that are over the equator. And geosynchronous are over the same spot on the Earth all the time. These orbits generally live in the 22,000, 23,000 mile altitude, so they can maintain their geosynchronous nature. Then there are circumpolar orbits. These live around 100 to 1,500 kilometers above the Earth's surface. There are sun synchronous orbits. They are near polar, but they do precess by a number of degrees every day, 1 degree, so it can maintain the same spot over the same location, the same time every day. And lastly, there are highly elliptical orbits. The Russian Molina orbit is used by their communication satellites. So it has a very close perigee to the Earth, and then it has a very elongated apogee. And as a communication satellite, that's what you want. It's a little cheaper than putting it into geostationary orbit. So another thing to look at is the edge of space. Where does space begin? We talk about putting things in orbit, but we have this atmosphere, that we need, that we breathe every day. So how do we know where space actually begins? So a fellow, Theodor von Karman, a Hungarian-American physicist, who was also the founder of the Jet Propulsion Laboratory at Caltech in 1944. He developed or postulated the Kármán line. And you'll see the Kármán line is dashed. And that's the maximum altitude at which you can get aerodynamic lift from a wing. Higher than that, you can't go. And if you're not traveling fast enough to go into orbit, you eventually will come back. And that's at, I guess the beginning layer, or almost the beginning layer of the thermosphere, which is where all of or most of the satellites live around the Earth. Beyond the thermosphere is the exosphere, and beyond that, beyond 10,000 kilometers, you end up in the solar wind. So there's influence there. So let's talk briefly about aeronautical flight. They're the first, I guess, high altitude and high speed airplane, or actually it was a rocket plane. It wasn't a jet engine, it was a rocket engine, was the X-15. In 1967, William Pete Knight piloted the X-15 at Mach 6.72, amazing speed. In 1963, Joseph Walker piloted an X-15 up to an altitude of 67 miles, which is just above that Kármán line. And later, pilot Mike Adams piloted it at 4,600 miles per hour just slightly more than the 6.72 Mach. Okay. The International Society has designated 50 miles as the altitude above which you can be considered as an astronaut. So the astronaut designation has been also awarded to Joe Walker, John McKay, and William Dana, because they had piloted X-15s beyond the 50-mile limit. In comparison, we look at the SR-71 Blackbird. It's a jet-powered craft, still pretty quick, but reaching only 2.9 Mach. And its highest altitude is about 85,000 feet, 16 miles. And then, of course, there's Spaceship One, which will probably be in the news again pretty soon. And it has potential to reach orbit. At least that's what the hope is. The highest flight it's taken is up at 62 miles, just at the definition of the Kármán line. And Mike Melville was the pilot, and he was the first commercial pilot to be designated as an astronaut. Now, related to the atmospheric layers, there is something called orbital decay, and this is important to know. We have, as I mentioned, 19,000 satellites up there, and we have quite a few that are very important. One of them is the space station. The ISS is in a nearly circular orbit at an inclination of 51.5 degrees. Its basic altitude is around a little more than 250 miles. It loses 50 to 100 meters per day in altitude. That's about 1 mile per month. Now, on board the ISS, wrong one. It has rockets to be able to restore the orbit. So there's no risk at this point of it crashing and re-entering the atmosphere. The Hubble is in a slightly higher orbit at 350 miles, thereabouts. And its orbit is decaying. Currently, 350 was the 2015 altitude. It's currently at 340 miles. That's the 2018. So it's lost 13 miles over 3 years. And it has no rockets or propulsion. So eventually it will re-enter the Earth's atmosphere unless we go up there and grab it and move it to a parking orbit or a higher orbit than that. So the next step is, how do we get into orbit? So assuming you have enough thrust, there are 3 variables you have control, or where you can have control: where, when, and how you launch. And that will define what your orbit is. The where component, it's very significant in terms of defining what your inclination is, your orbital inclination. And that has effects later on in terms of cost. So here are just a few of the rocket launch locations that can put objects into orbit. At the US, we have the Kennedy Space Center, of course, in Vandenberg in California. European Space Agency uses a location in French Guiana. The Russians have been using the Baikonur site since the beginning of the space race. China, India, and Israel also have locations. When the satellite is launched is determined by the launch window. And the launch window is basically what your intended purpose of the satellite is. What's your intended target or situation? So if you're scheduled to dock with the International Space Station, the launch time and direction needs to be planned to minimize flight adjustments that will be required to achieve the orbit. How the rocket is launched, will incorporate all the other variables, the duration of the burn, what the eventual final altitude is, what the launch azimuth is variable to some extent, so you can modify that orbital inclination slightly depending on the angle of launch. Just a quick note, Israel, for example, launches retrograde because it wants to avoid having booster rockets falling on politically unfriendly countries. So that's why it orbits retrograde or launches at retrograde. And you may notice that the International Space Station is pretty close to the inclination that the Russian rockets would achieve out of Baikonur. And that was done somewhat intentionally so that it would be less costly for the Russians and they would be inclined to participate based on that. Yeah. Sorry, guys, lost my my display. Where are we here? Okay. Here we go. Okay. So, good question. We're going to talk about Buzz Aldrin and Rendezvous. Well, we've covered a lot of background. But why Rendezvous? How'd that come about? Well, when we look at the mission to the moon, the lunar landing, there were a number of alternatives that were debated. Do we do a direct descent, like a lot of science fiction movies where a rocket lifts off, goes to the moon, the rocket lands in its entirety, and then takes off, comes back to Earth? Or do we do something called an Earth orbit rendezvous, where you park some stuff up in orbit, in Earth orbit, you rendezvous with it, and then you shoot yourself to the moon and you come back? And then there was the concept of lunar orbit rendezvous. And what's really unique about this is that you take only what you need to do the job. So you don't need to bring a big rocket to the surface of the moon. All you need is a descent device and something that you can ascend from, a platform you can ascend from, and go back, merge with another rocket that's going to then propel you back to the Earth. You don't need to bring a whole rocket to do that. So NASA engineer John Houbolt finally was able to persuade Werner von Braun and others of the benefits of the lunar orbit rendezvous approach. So the flight plan required an orbital maneuver that was theoretically feasible but not tested. And also some of the maneuvers would need to be performed in the moon's shadow and not visible from Earth, so you couldn't do radar tracking. This diagram doesn't show that. This was an early diagram, but in reality, when the lunar module lifted off the moon, they lifted from the Earth's shadow, so you couldn't see it. The closest analogy we had at that time to rendezvous were flight formations, fighter craft or bomber craft, and mid-air fueling. And more work was needed to be able to do rendezvous. So now we talk a little bit about Buzz Aldrin. I guess he came to the rescue. He was born in January 20th, 1930, child of the Depression in Glen Ridge, New Jersey. He got the name Buzz from his sister. His older sister could not say brother. She would say Buzzer. And so from then on, it stuck. And this must have pleased his father somewhat. His father was an aide to Billy Mitchell. And he also studied physics under Robert Goddard at Clark University. Buzz Aldrin played football at Montclair High School, and he was coached by Clary Anderson. And he was ambitious and assertive, but proved to be a team player taking on tough jobs. At 140 pounds, he played halfback and center. I don't think that would go well today. but that's what he did. Physics and math were his strengths, and he graduated third in his class in West Point in 1951. He joined the Air Force, flew combat missions in Korea, and was credited with 2 MiG-15 kills. He was awarded the Distinguished Flying Cross, Distinguished Service Medal, and later on the Medal of Freedom. He has a PhD in astronautics at MIT, and he is, well known as Dr. Rendezvous. He was part of the crew of Gemini 12, and of course Apollo 11. He's an author, a lecturer, as well as an advocate for space exploration. When he trained in the Gemini program, that program was designed to prove long duration flight, extravehicular activities, and rendezvous and docking techniques. He completed a 5.5-hour EVA. This was broken up into 3 segments, but that was the longest EVA at the time. He prepared and submitted his thesis. At the time, he was a 33-year-old doctoral student at MIT, and the title is Line of Sight Guidance Techniques for Manned Orbital Rendezvous. And this was extremely important given the mission of the Apollo at the time. So it's an extensive work. There are numerous examples examining all potential rendezvous approaches, including abort scenarios. And this was unique. He utilized computer simulations to test his hypotheses and show the value of automated tracking. Okay. The dedication in his thesis proved prophetic. He states in the dedication, in the hopes that this work may in some way contribute to their exploration of space, this is dedicated to the crew members of this country's present and future manned space programs. If only I can join them in their exciting endeavors. Well, he did. He was selected as part of group number 3 in October of 1963 and became an astronaut. Now, go back to the science for a moment. So here we have Orbital Mechanics 101. We've done a number of things. We've defined an orbit. We've defined the types of orbits. We've defined where the edge of space is, orbital decay, how to achieve and measure an orbit, and applying the laws of physics and to calculate orbital and escape velocities. We have one more concept, and that's the orbital mechanics. How do you change an orbit? So basically, the rule is that when you change velocity, it changes your orbit. So if here's my orbit is this blue circle, and I want to change the orbit, I add velocity. And what that will do, that will raise the altitude of every point on my new path, okay? And if I don't do anything, if I just let that go, I will return to the same spot where I initiated the burn. So basically, what a positive delta V, and we'll talk about that in a moment, what a positive delta V will do, it increases your apogee of your orbit and makes it more elliptical. The reverse is true if I were to make this negative delta V. What I would do is I would, at that point, decrease my perigee, and I would be in an orbit that would come in closer to the Earth. Okay. Now, one thing to note is that this change in velocity is applied tangent to the orbital direction and perpendicular to the orbital plane. So think of it as a record, an old LP if they're still around, So you're making that change in velocity tangent to the edge of that record. Okay. So here again, it just says a positive delta V in the direction of flight increases the orbital altitude at all points, except where the burn was initiated, and the negative of delta V is the opposite. The delta V was defined by Konstantin Tsiolkovsky, in the rocket formula, and that's what this formula here is. Relatively straightforward, basically saying that the delta V is equal to the velocity coming out of the rocket times the natural log of the ratio of the original mass, including all the fuel, divided by the final mass. So how do we now go from one orbit to another? HOHMANN defined what he called the transfer orbit in 1925. He was part of the same rocket club as Wernher von Braun as well. And this seemed to be a pretty straightforward approach and fuel efficient. And so what you do, this basically requires two burns, each 180 degrees apart. So we go back to the other diagram we have. So we add delta V here, changes the characteristic of our orbit. We raise the apogee. And now we do another burn at this point. So step 2, we do a burn here, which now again raises the apogee, raises all points in the orbit. And so now I'm in this new orbit. So the transfer occurred on this arc. I do another burn here, second one, and now I have this new orbit. So I go from this altitude to this altitude. So this is a little animation of HOHMANN transfer orbit to Mars. And it should be noted that HOHMANN transfer orbits are less useful in interplanetary trajectories because of the change in gravitational influence on the spacecraft as it goes from the Earth to Mars. The Earth's gravitational influence decreases. The sun's gravitational influence becomes a little more prevalent. And then finally, as it gets close to Mars, the Martian gravitational influence is more significant. And that changes this trajectory it's quite a lot. So the HOHMANN transfer formulas are cannot really be used for interplanetary changes. 1934, Ari Sternfeld defined what he called a BI-ELLIPTIC orbital change, and this is a 3-step maneuver. So here is your original orbit. This brown orbit is your desired orbit. Your first step is to accelerate, increases your apogee, do a smaller burn at this point, 180 degrees opposite, which now will bring you up slightly, not completely to a circular orbit. And then when you get to this point, you need to use negative delta V so that you would then achieve this particular orbital, orbit of circular orbit. If you didn't do that, you would take this path out here, and you would stay in that orbit. So you need to do a negative delta V at that point. There is also something called the Oberth effect or the Oberth sequence. And he postulated and actually proved that the increase in kinetic energy from a rocket burn is greater at high speeds than at low speeds. So what we talk about here is this process where you loop around, and every time you get to perigee, you add more delta V, which again is going to change your apogee, it's going to increase it. So you go around in this process and kind of slingshot your way out to where you want to be. So this is the orbital path that the Indian satellite Chandrayaan 2 took to get to the moon. Sort of like when you have a child or yourself on a swing, and every time you begin to come down and your velocity increases, you add a little push, and so you then continue to increase your altitude. So now we're getting ready to do a rendezvous, okay? So we know if we increase the speed, firing in a positive direction, you make it more elliptical and increase your apogee at the altitude. Okay, and as a result, your velocity increases due to the change in altitude. So you're basically your velocity decreases due to the change in altitude. So you're trading speed for altitude. And if you decrease the speed, firing in the opposite direction, you also make it more elliptical, decreasing your perigee and the altitude. And then as a result, your velocity increases, again, due to the change in altitude. So to catch up to a spacecraft ahead, we need to slow down. So you slow down to speed up. And the opposite is true. You speed up to slow down. So it's somewhat counterintuitive. Trading altitude for speed. So a good way to look at this is, here we have two situations in NASCAR and roller derby. They're kind of like on an inclined plane, so it kind of simulates a gravity well. So if you want to pass somebody, you move to a lower altitude on the inclined plane. You travel a shorter distance, you pick up speed, and this way you're able to move past somebody. Same thing is true for these old roller derby stars from the 1950s. You go to a lower location and you can go faster. And if you want people to pass you, you move to a higher location. Okay. Okay. So as a fighter pilot, Aldrin understood this relationship of turning radiuses and increasing speed, since he had been in a number of dogfights. So the next thing is, so we know now how we can change altitude, but what about inclination? Okay. And changing inclination is also important, because when you're launching to rendezvous with a satellite that's already in orbit, you may or may not be at a location that's going to put you in the proper inclination. So you have to be able to change the inclination. It is a costly process, though. The changing from, for example, a 28-degree inclination, which you would get launching out of Kennedy Space Center, changing that to a polar alignment of 90 degrees can cost as much fuel as it would require for a translunar injection. So it is a costly maneuver. So here you have, your original orbit, and now you want to have a more equatorial orbit. So you need to fire along this vector, which is different than adding altitude or subtracting altitude. You're firing now in a different plane from the usual that you would fire. You can also do the same thing in polar orbits. And this is an important and necessary maneuver during a rendezvous, because you want to achieve coplanar orbits between the target vessel and the interceptor. So let's talk more about Aldrin's thesis. So a couple of assumptions. He talks about everything is from the point of view of the interceptor. He defines the interceptor and the target. The target is passive. It stays in its current orbit without deviation. And the interceptor has the ability to measure the range, the rotation, phase angle, and the phase rate of the closure. And initial guidance positions are based on ground tracking, but thereafter, any correction in guidance is internal to the interceptor. The phase angle and phase rate are, he gives an example here, using two different parking orbits. These are temporary orbits before you do a rendezvous. And here he has a high parking orbit, which has a pretty low phase rate, 3.6 degrees per revolution. And here a low parking orbit has a higher phase rate, 21.6. So in thinking about this, I was trying to wrap my head around it. And the best thing I could think of is when you're driving down a parking lot and you see a parking space you want to move into, when you start your turn and how you start your turn and at what angle you're approaching the parking spot, kind of similar to how the phase angle and the phase rate changes. So it can be, you know, and he's doing it in three-dimensional space. Thankfully, we're only in two-dimensional space driving a car. So here's the rendezvous timeline that he defines in the thesis. And just before we get to that for a moment, just take a look. We have a number of different orbits here. You have your initial orbit after launch. You have now a parking orbit that you're waiting in, that you're sitting in. You then move to a waiting orbit, which is a little more circular orbit, and I'll explain why that's significant. And then finally, you do an intercept trajectory after you've achieved your line of sight guidance. So we start with the launch. Generally, you launch into an elliptical orbit. You circularize the, I'm sorry, I messed these up. Then you move to a coplanar orbit or a parking orbit. And that you may need to adjust the inclination in order to do that because you want both orbits in the same plane. Then you circularize that orbit with small changes in delta V to create a circular orbit. And that's your waiting orbit until you establish line of sight and radar telemetry. You confirm the optical alignment for the computer guidance, and then calculate your intercept trajectory. You initiate the terminal phase burn, or the TPI. You close in on the target, match velocities, and finally dock with the other satellite. Okay. What you're doing is essentially putting your craft on a collision course to be able to intercept the target vehicle. You can think of it a couple of ways. You think of two boats on the water. I don't know how many boaters are out there, but you're tooling right along and you notice that you have a constant bearing on another vessel and you're closing range. Well, that's a collision course. You could also think of it as, the calculation of the solution that's derived from a submarine firing a torpedo at a target. They calculate the speed and direction for that as well. Then at the final moments, what you do is you begin to slow down. You use these small thrusters to match the velocities, and then you can move into dock. So I've used this diagram in a number of the slides. I kept it here for this reason. So here's an example. This is where you begin, your line of sight. You establish radar control. You use your thrusters to approach the This is it looks like a Gina booster or some booster that the Gemini craft is going to dock with. This is not necessarily to scale at all, because by the time you start to initiate your transfer or your target orbit, intercept orbit, excuse me, you're going to do probably 90 degrees or maybe even 180-degree revolution. So it wouldn't happen in this kind of sequence exactly, but it symbolically gives you an idea of what's going on. So we talked earlier about coplanar orbits, and these are important because you want to be able to control the direction that you're firing. You don't want to have to fire in angles other than the angle that you're traveling in. So it makes better use of line of sight guidance. Your flight path is then generally in 2 dimensions, and the rendezvous point can be adjusted. There is something also called a chasing orbit, when you have 2 objects in orbit and they have different periods, they have different durations, they have maybe the same focus, so they're cofocal. You know, you'll notice one will revolve quicker than the other, and so you will catch up to the other object, and then you'll go past it, come back around again and again, so you can chase the other object around. The other advantage of a coplanar orbit is that the intercept phase can be delayed until the target is observed. This is the line of sight device. This is not the lunar module. This is the shuttle, but they use the same technique. And this is the ISS in the window that he's lining up with, getting ready to dock. Okay. This is what the lunar module looked like, returning, I believe. Yeah, it looks like it's returning to the command module. So it's on an intercept phase. Now, in the computer, what Aldrin proposed using were the Cloesi-Wilshire linear differential equations. And I'm not going to describe these to you at this point, but suffice to say that these are the second order derivatives of the 3 dimensions that the craft is being propelled in. So the computer logs the location of the target. It knows the location of the intercept vessel, and using these formulas calculates the trajectory necessary to achieve a rendezvous. So when we think about space exploration, the exploration of our solar system is complex. It requires large investments in design and engineering. Space exploration is a community effort. It's not like the early explorers that either rediscovered existing lands or traversed continental interiors or went on very risky ventures like Amundsen, Scott, and Shackleton. Great story if you haven't read stories about the exploration of the poles, both the North Pole and the South Pole. That's not the way to explore space today. It's essential to manage undefined contingencies and the margin for error, engineer for safety, and balance with the cost. So how did we get here? Defining orbits. Tycho Brahe, observing planets in orbit. Kepler, laws of planetary motion. Newton, the laws of motion. Tsiolkovsky, the rocket formula. Goddard, liquid fuel rockets. HOHMANN, the Hohmann transfer orbit. Oberth, the Oberth effect. And Sternfeld, the BI-ELLIPTIC. Von Karman, defining the edge of space. Von Braun, engineering and designing the Saturn V, as well as other rockets. Katherine Johnson, probably you all remember her from the movie Hidden Figures. Margaret Hamilton, not the Wicked Witch of the West. She was the program manager for the Apollo computer code, and she has all the piles of code listings. And I put him in here because it seems that we're at an age where we are having private investment in space exploration, and so one day Elon Musk will be in that Hall of Fame. I also wanted to just note, since we are talking about Buzz Aldrin, the astronauts who walked on the moon, and we have only 4 of them are still alive. So these are people that we owe a debt to in terms of lunar exploration. And we also have astronauts that orbited the moon. And you can see that Jim Lovell will have a birthday in about 5 days. And Borman had his birthday about 6 days ago. Ken Mattingly, interesting, is one of the few that orbited the moon on Apollo 16 and also has piloted a couple of shuttle missions. Buzz Aldrin, as I mentioned, a fighter pilot, decorated, combatant, Apollo mission, presidential medal, looking for further exploration, part of Gemini. And, although he was not the first human to set foot on the moon, he did earn a position of honor among scientists and engineers for his work on the practical application of rocketry, radar telemetry, digital computing, and with a dose of flying by the seat of your pants orbital dynamics, which made the exploration of the moon possible and beyond, hopefully. Thank you very much. There are some of the references. The thesis is available online. How Apollo Flew to the Moon is an excellent book. Some of the diagrams here were taken from that book. Von Braun has authored the Mars Project, and that's been reprinted in 1991, dates to 1953. And there are various Wikipedia articles and YouTube videos that are interesting to watch, especially those at the FAA.gov. Thank you very much.
All right. Thank you, Chris, for that presentation. We're going to be having a question and answer session now. I do have some questions that we have collected during the presentation. So I will start with the first one that I got. So keeping geosynchronous satellites in position requires fuel, and once you're out of thruster fuel and no longer are useful, are they moved into a higher graveyard or parking orbit? And about how many satellites are now parked?
To answer the last question, I don't know how many are in the graveyard orbit. It depends on the reason you decide on the graveyard orbit is because it's cheaper or less risky than allowing the satellite to fall back into the atmosphere. So there is a lifespan for any satellite, whether it's in geosynchronous or not, because at any altitude below 600 miles, you definitely have the effects of drag. At the 20,000 mile altitude, it's going to be less so.
All right. So our next question is about how long does it take the ISS to make one orbit?
I think I might have had that. I think it's around 90 minutes, considering the altitude it's in, and hold on a second. I'm trying to open the document. At that altitude, which is around at 350 miles, excuse me, 250 miles, It's traveling at around a little over 17,000 miles an hour. So it equates to about 90 minutes to be able to make a complete orbit.
All right. So the next question, and I had asked for clarification on this one, is are there satellites that don't actually orbit the Earth, meaning that they stay in sync with the Earth's rotation?
Well, I'm not sure I follow the question, but there are satellites that are orbiting the sun that are essentially in the same orbital plane and path as the Earth. There are points in the Earth's orbit called Lagrange points, where you could stay in that position because of the way the forces of gravity are balanced. So there's no force of gravity throwing you out of that location. So there are those kinds of orbits. I was reading recently one of the telescopes that was put in orbit. They wanted to try to create a situation where it was cooler and would not be subjected to the heat of orbiting the Earth. And so they moved it, outside of Earth orbit into more of a solar orbit within the Earth's same solar plane and same orbital path.
All right. I did find the clarification. He means there are satellites that stay in the same spot above Earth at all times instead of orbiting around Earth. And I believe what he's referring to is the geosynchronous or
That's
geostationary.
geostation.
Geostationary is the correct one.
Yeah. And that's used in a lot of weather applications, a lot of spy applications, being able to look at the same place, continuously to see what develops. So there is and also for communications, it's easier because you have a wider field of line of sight when you can bounce a communication signal off a satellite 20,000 miles up, and it's always there. So, I think your Sirius XM has a couple of different satellites out there. I'm not sure if any one of them is predominant over the other, but they are close to geosynchronous locations.
Right. So I'm going to put out if anyone in chat has any further questions, I ask that you put them now while I ask this next question. We have a viewer in chat who had done an experiment with their father where they moved a rubber duck with magnets. Can you use a magnet to move a spaceship?
Well, you need a big magnet because even small spaceships have a significant mass that if you wanted to have an impact or an effect similar to gravity, you're going to need a big magnet. Also, I mean, the Earth itself is a magnet. We've got a magnetosphere, so it is theoretically possible. Of course, with a large enough magnet, you can move lots of objects. But since it's not a separate planet, it would be hard to get a magnet that large.
All right, and in addition, I believe a while back, this is for the user who had asked that question. I had read something where they were testing possible forms of electromagnetic propulsion. I would suggest going with your father to look up those tests. And like I said, I'm not 100% certain on what they were testing that for or when they were testing that, but I do suggest that you look that up because that is not a topic that we are the most familiar with, unfortunately.
Okay.
But I thank you for the question. All right. So, while I'm just putting out a last call for any last questions in the chat. Um, I have a question for you. So, you've been an amateur astronomer for a while now. What caused you to get into this hobby?
Huh. That is a good question. It probably dates back to my days in elementary school or middle school. You know, when you first discover Orion, you know, it's the one that is easy to identify, and even in the light polluted environments of the New York City area, it's still somewhat visible. And I think I remember noticing that it would be every year it would be in the same spot year after year. So I kind of was interested in that, and then of course, being young kid at the time of the space exploration or space race, I remember Glenn's flight and staying home from school. I was not going to school that day. I wanted to watch this beginning to end. So I had a strong interest, probably going back to that time.
All right. So, just to give us a couple more seconds, I want to thank everyone who's tuned in. Please do check us out on our website, uacnj.org. All our information for public talks, our location and whatnot is available on that site. Also, a list of our further talks. We will actually, the first Saturday in April, be switching to the in-person talks at our location. We will be doing that through a reservation system because unfortunately we still are under COVID-19 restrictions. And just to keep everyone safe, you guys as guests and our staffing, because we're all volunteers, we do try.
Thing I'd like to add, if I may,
Sure, not a problem.
okay. For those who are interested, uh, there are some orbit simulators programs out there. The probably the most popular one is the Kerbal Space Program. It's designed for Xbox. I've seen demonstrations of it. I don't have an Xbox, but it looks very interesting. You design complete flight path. You have different planets you can visit. There's another one called Reentry, and then there's NESSP Orbiter. I've used Reentry, and I either crash back into the Earth or I go into an escape velocity. It's very challenging to try to, simulate or reproduce a lot of these maneuvers that we just talked about. But I think that could be fun for a lot of people.
Yeah, I have actually personally played the Kerbal Space Program, and that is also actually available on PC.
Uh,
Um, at least the first game. I see right now you have up there that there is a Kerbal Space Program 2, so I'll have to look that one up because I did enjoy the first Kerbal. But like you said, it actually has a lot of the science that you went over tonight. So that's an excellent program to kind of get a feel of how much actually goes into launching a vehicle and doing orbits and sending it to other planets. So, since there doesn't seem to be any more questions, I want to thank everyone for tuning in. And until next time, have a good night.
Thank you.